All right, recording started. All right, hello everyone, welcome back. Thank you so very much for joining us. We have a very exciting seminar today by Dr. Yiling Zhang, who is an assistant professor in the Department of Industrial and Systems Engineering at the cold at the time under snowstorm University of Minnesota. And she received her PhD in Industrial and Operations Engineering from the University of Michigan. And as she will tell us a little bit about it, she has very interesting research topics, including stochastic programming, integer programming, and nonlinear programming. And also, of course, applications to various complex, for instance, service systems, including transportation, power systems, and healthcare. But today she's gonna tell us a little bit about bilevel programs and how to incorporate uncertainty into bilevel programs. So very much looking forward to it. Thank you so very much for joining us, Yiling, and for being a part of our seminar series.
Thank you so much, Mary, for the nice introduction, and also thank you for everyone for having me for being part of this seminar series. So I'm Yiling Zhang, assistant professor from University of Minnesota. Actually, we're not that cold this year. We just got our first snow yesterday. So my talk today will be about bilevel programs under uncertainty, including models, algorithms, and applications. So let me first get started with the decision dynamics of this stochastic two-stage bilevel programming structure. So this is actually a generalization of stack overflow again. So where the leader first make a here and now decision, and then the uncertainty will reveal. And the follower would observe both leader's decision and the uncertainty. And the follower will make their wait and see decision based on their own interest. So this type of decision dynamics can be found in many applications ranging from transportation to machine learning. So let me give a few examples here. So the first one is a facility location, where you can see this type of bilevel structure helps to describe the behavior of the customers and also the leader, which is a service provider. They try to design their system according to the customer's behavior. So in this problem, here we have a few stores already in the market. There are some demand locations. So the leader of the problem is actually the new company who wants to join the market. So they want to know where they're going to open their stores. And after they build their stores, the customers, which could be individual customer or aggregate customer, so they will observe the stores and make their decision of where they want to make their purchase. So their objective could be trying to minimize their total transportation cost. So in this problem, the uncertainty could be mainly from the customer side. The second one is in the power distribution system. So for the distribution system operator, they make operational decisions, including energy procurement, battery configuration, and also pricing decision. Because nowadays, many residential households, they have those smart sensing and metering devices, which can help them to adjust their electricity consumption according to the prices. And at the same time, in this distribution system, normally there are some distributed energy resources in the system, which are likely to be from some renewable energy. So it's actually encouraged if those renewable supplies can be consumed locally just within the distribution network. So in this system, the distribution system operator is the leader of the problem, and their pricing decision would impact the customer's electricity consumption. And the uncertainty would be from renewable energy, and also there could be some environmental parameters such as outdoor temperatures. And also you can find this type of a customer's behavior being modeled in public transit systems. So the transit agency, they want to design a multimodal transit network. And the design of this network would impact the rider's decision on which route they'll take from their origin to their destination. And the uncertainty here would be from the traffic condition and also from the demand of the riders in the system. And the last example is from machine learning for hyperparameter tuning, considering a support vector regression here. The leader here would try to minimize the out-of-sample error by setting some parameters in the regression model. However, the follower would have a different objective, which tries to minimize the in-sample errors given the parameters for the problems. So for all these applications we have seen so far, they can actually be captured in the two-stage stochastic bilevel programming framework as following. So this optimization model is actually from the leader's perspective. So the leader tries to minimize their direct cost of their decision X and expected indirect cost. So this indirect cost is impacted by the leader's decision and also the uncertainty. The leader's decision is actually reflected in the follower's optimization problem. It would impact the right-hand side and or the object coefficient for the follower's problem. And the follower's solution may or may not have the same contribution to the leader's problem and to the follower's so may or may not have the same contribution to the follower's problem or as the leader's problem. So in the case, if they actually equal to each other, then this problem would reduce to a general two-stage stochastic program. But in a more general setting, when they do not align with each other, then there could be a different attitude from the leader towards risk here. So when the follower has multiple optimal solutions, if the leader believes the follower would always pick the solution which is in favor of the leader's decision, then we would have an optimistic variant of the problem. But if the leader is risk averse, if they assume the follower would pick the solution which is against their decision, then we would end up with a pessimistic variant of the problem. So in the later part of this talk, we'll assume all these objective coefficients and the right-hand side, they are actually linear in the uncertain parameter and linear in the decision X here. So for the stochastic bilevel programming problem, when there's only very limited amount of samples available, then the out-of-sample performance of the solution may not be very consistent. So for example, this is a two-stage stochastic bilevel programming model. We can see that when we have like very limited, like 10 or 100 samples, then their out-of-sample performance could vary a lot here. So then instead of assuming some like specific distribution when we have very limited number of samples, we'll employ this type of distributional robust variance of the problem. So now the leader actually minimize the worst case expected indirect cost with respect to the distribution within this ambiguity set we construct. So this set actually contains all the plausible distributions people believe may be of the true underlying distribution here. And also we have the following two assumptions. First of all the object coefficients and right-hand side coefficients, they are square integrable. And second, we assume relatively complete recourse. That is for every like feasible leader solution X and for every realization of KC. The forest problem always has a non-empty and bounded feasible region. So for the two-failed bilevel programs and distributed robust optimization, so both of them standalone actually have attracted lots of attention in the past years already. So the study of deterministic bilevel program actually can be dated back a few decades ago, but most of work there about optimistic version of the problem. Very few works such as Vismet or the considering the pessimistic case. And also I want to point out a very like recent work listed here by Georgia et al. So they trying to draw the connection between bilevel program and robust optimization. So they actually show that under certain cases, you can have the reformulation from one to another. And in recent years, there are like some work concerning the bilevel programs under uncertainty. But still, again, most of them are about the optimistic version of the work. I want to point out the work by Yiling and Quinn. They actually studied the decision rule bounds for stochastic bilevel programming, both for optimistic and pessimistic case. And the last one listed here is actually a very recent survey paper about bilevel programs under uncertainty. And of course, there's a growing amount of research on distributed robust optimization in the last decade. So the purpose of this talk, I just want to introduce some of my ongoing work regarding distributionally robust optimization and bilevel programs. So the first part of this talk will be based on pessimistic model. We are looking for decision rule approaches to provide bounds for pessimistic bilevel programs under moment ambiguity. And the second part of the talk will be about an optimistic model, which is motivated by a distribution network problem. And we're going to consider veracity ambiguity. The ePrint will be shared soon. So let's first start with this pessimistic case. So as we mentioned earlier, when the leaders and the followers' objective coincide, the DR bilevel program is actually reduced to a two-stage stochastic program. So it's not only the pessimistic case, but actually the optimistic and pessimistic case, they reduce to the same DR two-stage program here. So starting from here, you can use your favorite tool, either like using decision rules or using some decomposition method to solve this DR two-stage stochastic program. What we are interested in is a more general case when the leader and the follower's objective do not align with each other. So the challenging of this case is actually from how we actually take care of this arc-mean constraint or this set membership constraint here. So we first introduce a optimal value function here to denote the optimal value of the follower's problem. And then we can actually replace this set membership constraint with the following constraint by imposing a feasible y to the follower's problem with objective to be no more than the optimal value of the optimal value function here. Then combining the object here, we actually have a linear optimization regarding this decision y here. So we can take a dual of this problem, we obtain the maximization problem here. And the lambda and p are the dual variables associated with the two constraints here. So in this formulation, now we actually can substitute this optimal value function back to this minimization problem. And then this minimization can be combined within the minimization here. But there's actually an issue with this formulation, that is, we can see lambda, x, and y here, they're all decision variables. So we actually end up with some trilinear terms. So what we actually show in our work is, so the bilevel structure in the second stage problem can actually be transformed into an equivalent single level structure. And in this reformulation, we actually eliminate that trilinear term to bilinear terms by doing some variable substitution. And another thing we've done here is lambda now is no longer a recourse decision, but a first stage decision. So in other words, we show that for every like realization conceit, they actually share the same dual variable lambda. Therefore, we can move this minimization of lambda from inside the expectation to the outside here. And this results actually hold for ambiguity set that is convex and weakly compact. So this mild assumption is met by many like commonly used ambiguity set. from like moment-based to versatile to some discrete distribution supported compact sets. But still, this formulation would have a bilinear term. So later on, we'll focus on the case where X is binary. And also I want to point out, because we move this lambda to the first stage, so later when we derive the decision rule bounds, then the formulation will give tighter bounds there. So the moment-based ambiguity set we consider are actually built based on two moment estimators obtained from historical samples. So we have this empirical mean and empirical covariance matrix. So when there are not enough samples, then people may not trust this two moment estimator much. Therefore, in this moment-based ambiguity set, there are two parameters, gamma 1 and gamma 2, which control the confidence level of the empirical mean and covariance. So intuitively, the larger values of gammas, then more uncertainty we actually assume around these two moment estimators. So for this two ambiguity set, the first one actually assumes a continuous polyhedron support set, and which we assume is compact here. And the second type of ambiguity set assume a finite discrete support set for the random parameters. So we'll have our discussion for the two cases. For the first one, where we have continuous support, we'll employ the linear decision rule to provide upper bound for the DR bilevel program. So after we apply the linear decision rule, there are actually a few challenges. First of all, we still end up with bilinear terms, but those bilinear terms always involve the binary decision X with decision rule related variables or the lambda. So we can actually provide linearization using Minkowski envelope and inequalities. And constraints 3 and 4 here, they're actually semi-infinite constraints. So, but we can use the classic robust optimization techniques to provide finite reformulation for them. So the real challenge is actually from the first constraint here, because the quadratic matrix here may not always be convex here. So this is a non-convex constraint. And this non-convexity is in fact just inherited from the bilevel structure there. So we have a very naive way to approximate this non-convex constraint. The first is just to assume, although it's non-convex term, but we assume this is a convex term. So we'll have a 0, 1, a semi-definite programming approximation. And an alternative approach is we try to utilize the modern copositive cone techniques, which actually provides us equivalent 0, 1 copositive reformulation. Although this is a convex reformulation, it's actually inattractable. So we still need to use a 0, 1 SDP approximation to that. So we actually end up with two 0, 1 SDP approximation. Both of them provide upper bounds for this DR bilevel program under continuous support. The third method we try here is to have a contemplative method. This is motivated by Yiling Zhang and Quinn's work, because their result actually suggests that if we know the mean and covariance matrix of the distribution, we can derive an upper bound by solving a mixed integer linear programming formulation. So therefore, the contemplative method is just to iteratively separate the moments from this projected moment uncertainty set, which is derived from the distributional ambiguity set there. So far we obtain the upper bounds using different approaches. But if we look at the support, discrete support, in fact, we can derive the 0, 1 SDP exact reformulation if the discrete support is exact. So naturally, this provides us an idea to derive a lower bound for the DR bilevel programming under continuous support. So we can actually just draw the samples from the continuous support and use those samples to construct the discrete ambiguity set, which then would provide a lower bound for the DR bilevel program. So to summarize what we have so far is we actually have three approaches which provides upper bounds for the DR bilevel program. The first one is a naive 0-1 SDP approximation by assuming the non-convex constraint is actually convex. The second one is derived from the 0-1 copositive reformulation. The last one is a cutting plane method. And the lower bound would be derived based on the discrete ambiguity set with samples drawn from the continuous support set. So then we'll test this three upper bounding techniques on a facility location problem where we have 8 locations of demand, and there are 6 candidate locations for opening store, assuming one is already occupied by a company. So company B is the leader of the problem. They want to know where they're going to open their stores among the other 5 locations to maximize their total profit. The customer here is an aggregate customer who wants to minimize their total transportation cost. So here is some computational setup. The first result we have here is just to compare the approximation power of the 3 upper bounding approaches we derived before. So here we have tested instances with the uncertainty only in the forest constraint, as the uncertainty in both the objective and the constraints. So we can see that for both cases, the MIP-based cutting plane method actually provides much faster computational time compared to other methods. And we also calculate the approximation gap based on the difference between the upper bound and lower bound. So the cutting plane method also provide better approximation gap. But in general, when we have uncertainty both in the objective and constraints, it takes a longer time to solve, and also the approximation gap is not that good, as we only have uncertainty in the constraint. The second result is to show the solution details when we have different parameters for the ambiguity set. So the larger values of gamma, the more uncertainties we're taking into consideration here. As we can see, when we increase the value of gamma, the total profit is actually lower because more uncertainty is considered for the decision there. And we have this out-of-sample performance comparing the stochastic bilevel programming with distribution robust variant here. So we have 2 different parameter settings for the distribution robust optimization model. And still under the 2 cases, we can see the distribution robust optimization model with carefully chosen parameters actually provides much more concentrated out-of-sample performance compared to stochastic bilevel program. So for the second part of this talk, we actually have an optimistic bilevel programming model, which is motivated by this distribution network problem here. So the upper level is the distribution system operator who wants to decide the operational decision to minimize their total operational cost while respecting constraints of power flow balance and voltage limits. So the decision are mainly for real-time pricing and power purchased from the wholesale market. So in this problem, we actually assume we have multiple folder or multiple household with HVAC system, which can provide controllable electricity load here. But because we assume all those folders, they do not communicate with each other, so they are independent folders. So in this case, we can actually show this folder can be viewed as an aggregated folder therefore we still stick with this one leader and one follower setting for this problem. So the follower, they are the residential household who would adjust their electricity assumption according to the pricing decision. And their objective is trying to trade off between their electricity bill and the thermal discomfort while respecting some thermal equation here. And their decision would be the electricity consumption, which would be a demand response signal that is fed back to the distribution system operator. So the uncertainty in the system involves solar PV generation and outdoor temperature. So here's a optimistic formulation here. So now instead of having a maximization, we have a minimization for the second stage problem. And also I want to point out the pricing decision only impact the objective of the followers because the follower wants to trade off between their total electricity bills and the thermal comfort. And one more difference here is we actually include some linking constraints. So in this second stage minimization problem for the leader, we have a constraint which links the decision of the leader and the follower because as we can see, the electricity consumption, which will impact the flow balance constraint for the distribution system operator. So that is one of the motivation we have the linking constraints here. So based on this formulation, then we focus on this versus 10 ambiguity set, which is built based on historical samples. We'll obtain this empirical distribution based on historical samples. And versus ambiguity set is a ball constructed around this empirical distribution with a radius epsilon here. So we can say if epsilon is 0, then this versus ball will just reduce to a singleton, which only contains the empirical distribution. So based on this versus ambiguity set, we can show that this distribution robust bilevel optimization problem still enjoys those good data-driven properties as their like single level counterpart. So here we denote the Jn and Xn as optimal value at optimal solution obtained from the DR bilevel program under versus ambiguity set. So N here is to emphasize that the optimal value and optimal solution they're obtained based on the N historical samples. So the first property here is if we have a carefully chosen radius with a confidence level beta n, then the worst case expected objective obtained from the model actually provides 1 minus beta n upper confidence bound on the out of sample performance of the solution here. So this guarantee is derived according to the properties of the versus ambiguity set. And what's more we can show here is if we have more historical data available, if the sample size tends to be infinity, then the data-driven worst case expected objective as a solution actually converge to the optimal value at solution with the true underlying distribution. So the proof is based on showing the second stage recourse problem actually is Lipschitz continuous in the random parametric C and lower semi-continuous in the first stage decision X0. And furthermore, if we have a binary decision X and discrete support, we can derive exact mixed integer linear programming reformulation. And this is achieved by replacing the argmin constraint with strong duality-based optimality condition, and also we linearize bilinear terms in the formulation here. So then we have this case study for this 33 bus distribution system with 5 demand location. And bus 1 is actually connected to the wholesale market. And this is operated from 9 to 5. We are looking at the impact of different penetration of renewable energy here. So we compare when we have lower renewable penetration versus higher renewable penetration. Here are 2 types of curves showing in the plot here. The first is this yellow bold line here. It's the hourly pricing decision. And the other curves, they are reflecting the electricity consumption from the residential household. So in general, we can see here, when we have higher renewable penetration, the hourly prices tends to be lower, and also more electricity are consumed during the peak hour of the solar PV generations. Therefore, this is consistent with our initial idea, trying to provide demand response to consume those renewable energy locally. And here is one more factor we're considering here is the household, they may have different cost and comfort trade-off. So for the household who are actually tight in their budget, so they would focus more on the cost. They actually do not enjoy as much financial benefit or thermal comfort compared to those households who are not that tight with their budget here. So one takeaway message here would be when we have those Bilevel programming models, it's very important to have some equity constraint to impose that the heterogeneous followers, they actually enjoy equal benefit from the system. And another result here is the out-sample performance comparison between the DR model and the robust optimization model. So overall, we can see for the DR model, they actually provide financial savings for both the leader and the follower in the problem, while guaranteeing the same thermal comfort level for the follower here. All right. So to summarize, we have investigated pessimistic and optimistic Bilevel programs with binary leaders under distributional ambiguity. For pessimistic case, with deriving upper and lower bounds using as the rule SDP approximation and cutting blend method. For the optimistic case, we show the desirable data-driven properties, including out-of-sample guarantee, asymptotic convergence, and tractable MILP reformulation. The case study actually have revealed very complicated interaction between uncertainty and followers' behavior. So for the future research direction, we're interested in, although we have the exact reformulation when we have discrete support, but if we have more data samples available, still it could be hard to solve it. So we're looking for some decomposition method. And the second interesting direction is we can see for all the results we derived before, they are based on some continuous followers decision variable. So when we have discrete follower, then the previous approaches, they do not apply anymore. So we're looking for some piecewise constant decision rules, and hopefully those rules can provide tractable solution approaches and also some expandability to explain the interaction between uncertainty and followers. And the last research direction is, so far all the discussion is based on the followers, which do not really talk to each other. But in many applications, we can see the followers, they may exchange information in certain way. Then they have the dependent structure. So how we can consider those dependent structure in this type of problem? all those are pretty interesting, like future research directions. All right, so this is all of my talk here. I'm very happy to take any questions.
Thank you so very much, Yiling. Very, very interesting presentation. And thank you so much for leaving so much time for interactions, questions. So I will stop recording so that